Hello, greetings to one and all. This is the midterm presentation for the Motion Planning Group project. The topics that we have chosen to work on is constructing a Watchmen road for an indoor environment. I'm Shreyas and my group members are Rutvik and Sairam. Let's get right into it. The problem that we are trying to solve is we want to try and find the Watchman route when only the area of a map is given by using the optimal position of the static guards. And the motivation that we have for this problem statement comes from the classic art gallery problem and the Watchman route problem. The art gallery problem is a problem used to determine the minimum number of guards that are required or are sufficient to cover or see every point in the interior of an art gallery or a museum. Whereas the Watchman route, what the Watchman route problem is an optimization problem in computational geometry, where the objective is to compute the shortest route a watchman should take to guard an entire area or to guard every single edge, or it should visit every single edge with obstacles only when only the area of the map is given to it. An indoor environment can be viewed as a polygon with holes or without holes, and for a polygon with total n vertices and the guards as points inside the polygon or on vertex of the polygon or even moving inside the polygon. Any point P in the polygon is said to be visible from a guard G if the line segment joining P and G does not intersect the exterior of the polygon. There are different types of guards. So there are four types of guard. Vertex guard is a stationary guard present at the vertex of the polygon. A point guard, which is a stationary guard present anywhere inside of the polygon. A mobile guard is a guard that moves anywhere inside the polygon, given that it does not hit any obstacle. And edge guard is a guard that moves along the edge of the polygon. So the related work that we have studied so far, and it has been done on the art gallery and Watchman route, some of it has been listed here. There are plenty of papers that you can go through, and the list is just endless. Here are the few papers that we found were quite relevant to the work that we proposed to do. So the first one is that the art gallery problem was first proposed by Victor Klee in 1973 for stationary guards. A solution to this problem was given by Vasek Chwatal in 1975, who gave a proof for and a theorem which says that guards are n by 3 guards are occasionally necessary and always sufficient to cover a polygon of n vertices. Recently, many people are trying to improve the time complexity of the solution to the problem, or are coming up with new ideas or extensions of the art gallery problem like chromatic art gallery problem and Watchman route problem, which help in minimizing the time complexity, thus saving space and overall computation power that you need for your computer to run this code. Also, most of the researchers on art gallery problem have given solutions which involve conversion of the polygon into small convex structures, and followed by the guard search, which may or may not give the best solution to art gallery. Whereas we try to find the best solution to art gallery problems using diagonals in the polygon to find the guards and do not convert the polygon into any convex structure. Computational geometry also has a classic problem known as the Watchman route problem, which is to compute the shortest path that is constrained in the boundaries of a polygon P so that every point in P is visible at some point when traversing through the route. The Watchman route problem is an important model in the field of robotics in which a mobile robot is used to do inspection of a part domain when the robot is given in only the area of the domain. This is a very up and coming hot topic in mobile robotics. There have been many theoretical papers on the most optimal way to find the shortest route for the Watchman route, but in the reviews that we have done so far, no one has done so in simulation to prove the same. Thus, this is a sort of brand new novel area of research, and we hope to scratch the iceberg of it. All the algorithms given in this paper so far were approximate algorithms, and thus there exists no guaranteed algorithm that we can follow to find the optimal Watchman route. The approximate algorithms are such as the line of sight algorithm, which discretizes the grid or uses lemmas to find theoretical proof. We use the actual geometry of the map to try and build a path using these methods, and we are trying to compare the method that we propose to the theoretical methods that have already been done, and compare our time complexity and our results with them. So this is the proposed approach, how we plan to find the final path for a Watchmen route. First, initially we'll find the static stationary guards by finding the solution to the art gallery problem, and then we'll try to find the Watchmen route using the stationary guards, and we'll try to connect the stationary guards. And our logic is that if the stationary guards are at their optimal location, connecting them in the shortest possible path should also ensure that the watchman, if he traverses this path, will guaranteedly view every single edge of the polygon at least once. This is in As far as we have researched, this is a novel approach, and we came up with a solution just like I introduced a while ago. And so far we have in our project, we have so far done the art gallery problem, and we have found the stationary guards needed in their optimal locations using methods that Rutvik will now explain. So this is the general proposed approach, and I'll now pass it on to Rutvik. Thank you.
So now that we have learned about art gallery problem, stationary guards, Watchman route problem, we will now move our focus to the placement of static guards. Before moving to the algorithm to find minimum number of static guards, it is better that we first understand where we can place the static guards. So there are various methods where we can place the static guards as shown in this slide. So these methods are the Voronoi diagram. That is, we can place the static guards on the Voronoi diagram. As we can see in the first figure, the blue polygon has Voronoi diagram with orange vertices. So what we can do is we can place the static guards on the orange vertices of the Voronoi diagram to guard the polygon. Second method could be that we can place the static guards on the skeleton of the polygon as shown in the second figure. The blue line is the skeleton of that polygon and the red dot is the stationary guard. So in the third method is the dual tree method, which, which depends upon triangulation of the polygon. We can place the static guards on the dual tree as well. Then we can place the static guards on the shrinked polygon. So basically we can reduce the dimension of the polygon and shrink it, and then we can place the static guards on the shrinked polygon as shown in the fourth figure. The red figure is the shrink polygon. And then finally we can implement the triangulation method. So basically we can convert the polygon into small triangles, and then we can place the static guards either on the center of the triangle, on the vertex of the triangle, or on the circumcenter of the triangles. So these are various methods where we can place our stationary guards in the polygon. Now that we have found that where we can place our stationary guards, let's find minimum number of stationary guards that we can place using these methods. So the algorithm for this is in the next slide. Yeah. So this is the theoretical algorithm that we have proposed for finding minimum number of static guards to guard the complete polygon. So the algorithm starts with creating a polygon. And in this case, we have considered the example of Voronoi diagram. In the second step, we can see that the second step finds the Voronoi diagram. But instead of Voronoi diagram, we can also use the dual tree, triangulation, skeleton, string polygon, anything. But for this case, we are considering Voronoi diagram. So in the third step, what we do is we initialize an open list and append all the vertices of the Voronoi diagram to that open list. And then in the fourth step, what we do is we find a vertex on the Warner diagram such that it guards maximum of the edges of the polygon. And then in the fifth step, we find the edges which are unguarded by the previous vertex V1. Then further in the sixth step, we find another vertex V2 which guards maximum of the remaining unguarded edges. So we continue this fifth and sixth step until we guard all the edges of the polygon. So this is very simple method or theoretical algorithm which we can say for finding the static guards. And the figures also give us an idea of how the algorithm works, starting with polygon formation, then Warner diagram, then finding of guards, and then final placement of guards on the Warner diagram. Now we'll look at the experimentation. Now, in the previous slides, we saw so many methods like Warner diagram, string polygon, skeleton, triangulation, dual tree. Now, which method should we prefer and which method we should not? So on implementing all the methods above, we found that Warner diagram gives us the best solution and the non-varying solution. Actually, every polygon has only one Warner diagram. The Warner diagram doesn't vary, and therefore, as it doesn't vary, it doesn't gives varying solution. Repeatedly, it gives the same solution, which is a good thing for our results. But there are other methods such as dual tree, centroids of triangle, circumcenters of triangle, which give varying solution. Now in the bottom three figures, we can see same polygon has three different dual trees. So three different solutions, which means that we don't know which is the better solution, which is the best solution. So it is very difficult to find out which solution will be the best for us. So hence we conclude from our experimentation in the initial part of our project that finding and placing the static guards on the Warner diagram is beneficial as compared to other methods. Now that we have found the static guards, we'll move our focus to connecting these static guards, that is the Watchmen route. So there are various methods that we can use, such as the Warner diagram approach, or discretizing the environment and using A-star algorithm. Then sampling, other methods of sampling such as Gaussian sampling and bridge sampling. So we can implement various path finding methods. Although this part of the project is yet to be implemented, therefore we are not specific about which method is the best for connecting the static guards. And therefore we are just mentioning which methods we can use. We are going to implement maximum of these methods, and then we are going to compare and see which method gives us the best solution. Now in the further slides, the extended goal of our project will be explained.
Thank you, Rutvik. So now we move on to the extended goals of a project. Our first extended goal is to include holes within the polygon which are represented as red colored polygons, which will further increase the complexity of the problem in terms of vertex finding and path determination. As discussed before, we create a Voronoi map for these polygons, which is followed by optimal path search algorithms to determine the Watchmen route. So while drawing the path and while determining the vertices, we consider these red colored polygons as obstacles, and none of the vertex of the Voronoi map should fall within the polygon, the red colored polygon. And also the path is traced in such a way that the red colored obstacles are avoided and a suitable optimal route is found. So that's it for the first goal, and now let's move on to our extended goal number 2. So the extended goal number 2 deals with introducing introducing intruders in the presence of mobile guards in the map. So here we introduce an intruder as a random point in the map we set a goal point for the intruder as well as a starting point within the Voronoi map. As far as introducing the number of mobile guards is concerned, we start from a minimum value which is lower than the numerical determined minimum number of guards. Here it should be less than n by 4 mobile guards for a general polygon and 3n plus 4 by 16 mobile guards for an orthogonal polygon, where n represents the number of sides of the polygon. So before we move on, there are two important terms to know about. The first one is reflex vertices, the second one is star regions. Reflex vertices indicate the number of sharp corners within the polygon, as we'll see in the next two slides. And star regions are obtained by extending these edges associated with the polygon beginning from a reflex vertex. Yeah. So we need to know the procedure for finding the optimal number of cards, isn't it? So yes, this is achieved by minimal partitioning. So what we do is, when we are given a polygonal map with obstacles or without obstacles, we first divide it into multiple smaller polygons, namely pentagons, hexagons, octagons, nanogons, and so on. And each partition is given a guard, and these guards guard the particular partitions depending upon the number of vertices and relative placement of the star regions, which decide the number of guards. Let's continue. Yes, so we need to know the number of mobile guards that will be required to track an intruder, so to follow an intruder and catch it when an intruder is introduced. We'll look into further details about the path planning for intruder in the coming slide, but before that, no, we'll see it in this slide itself, but before that, we plan to track the intruder and catch it, right? So we follow the steps followed in task 1, which Rutvik has spoken about, to determine the optimal path for the mobile guards, which is the Watchman route. Next, as the Watchman, so Rutvik has spoken about study guards, which move in a path, hence making a mobile guard. Yeah. So next, as the Watchman begin to traverse and monitor the polygon, the vertices of the polygon and the edges of the polygon, we introduce an intruder at a blind spot where the guard cannot see or monitor at the particular moment, randomly chosen. Yeah, and the intruder, which is placed in a random point, receives the data of the visibility of the mobile guards, including the edges and the vertices that are being currently monitored, to plan a path according to bacterial potential field or pseudobacterial potential field algorithm. So the specialty of BPF is that, or BPF is that, it overcomes the local minimum problem which is faced in artificial potential field, and also this algorithm finds out the best gene or the best set of parameters that can help us find the appropriate path. So we'll look into the details of BPF algorithm later on, and as of now, these visible regions of the guards are plotted as obstacles in the map of the intruder. So the map is dynamically updated and the path is planned in such a way to dodge the obstacles according to bacterial potential field algorithm. So why we have gone for potential field method is because if we go for RRT, for example, we need to update the path frequently because the obstacles change, right, dynamically, and the range of the obstacles is so huge that we might not find a viable path at all. So what we do is we employ a potential field algorithm, namely PBPF, pseudobacterial potential field, which help us avoid local minimum and unreachable target goals, and so we can give a certain wait time for the robot until which it can stay in a particular position out of sight of the robot, and as the robot moves away after it has tracked a particular number of vertices, it can continue its traversal until it reaches the goal. It's interesting, right? And whenever the intruder reaches the obstacle for given n randomly chosen starting points and goals, we can slowly increase the number of cards by 1 to an optimal value, which is a numerically determined value, as shown in the research papers. And our project is about finding, at least the extended goal of the project is about finding an optimal number of guards, which is even lesser, or which is the minimum when compared with the values determined in the research papers, uh, which depend upon the number of sides of the polygons, as we have seen before, 3n plus 4 by 16 and n by 3. Oh yeah, now let's move on to the algorithm itself. So I have shown a diagram on the left hand side here. So I'll just describe it about it briefly. So here we can see an octagon, which is not a traditional octagon, but it's rather a convex octagon. Yep, not a conventional one. So here we can see 3 points, O1, O2, and O3, right? So as I had already described, we have two important terminologies: reflex vertices and star regions. So here O1, O2, and O3 represent the reflex vertices of the polygon. So we can see that from O1, O2, and O3, we can draw out regions which which can capture most of the other areas of the polygon. Whereas if you want to draw out, if you want to choose the right hand side corner as a vertex, it can cover only that particular region. But by doing this, we can create dynamic regions which are represented in green color, such that the robot can never start from one end and reach to the other end. So this is the advantage of reflex vertices, and the shaded regions in the, what do you call it, the shaded regions in black lines, in space of black lines, represent the star regions. And here dynamic, let me explain about dynamic regions. So whenever we introduce an intruder to the map, uh, a guard will never start tracking it unless and until it touches, or it touches the border of the dynamic zones or enters the dynamic zone. So the purpose of dynamic zone is to reduce the so-called reduce the complexity of the problem by allowing the intruder to traverse for some amount of time, and then the guard can catch it quickly as it enters, because it can never reach the goal, uh, provided the goals and the starting points are at the opposite ends. It can never reach them, and before it reaches, it can track it, right? And H1, H2, and H3 are three feasible points where the guards can be introduced so that the intruder can be tracked. So the blue dotted lines represent the roadmap that has been achieved. So now I'll explain the algorithm. So as I have already explained, the minimal partitioning of the polygon uh, is the first concept, is the procedure for employing the mobile guards to track down the intruder. So first we partition the polygonal map into polygons of smaller sizes, namely hexagons, septagons, octagons, and so on. And yeah, this is called minimal partitioning. And next we need to determine the minimum velocity of the guard needed to track the intruder. So we are given the polygon and the initial position of the intruder. And only when the velocity of the guard is greater than that of the intruder, it can track it down, right? So after minimal partitioning, we follow the rules for deployment of guards in the corresponding polygons. So these rules are nothing but these rules decide the number of guards that can be placed within a particular region, right? So a guard can track the speed of the intruder if its maximum speed, only when its maximum speed is greater than the maximum speed of the intruder, right? And next we compute the maximum required speed of the guard and the roadmap determined based on the dynamic zone. So we determine the roadmap as well as the maximum speed of the guard. And this maximum speed of the guard should be kept as minimum as possible to avoid what do you call it, to save the energy in real time and computational time in simulation. And this is repeated for all the small polygons until the intruder can no longer escape. So yes, that's it. So here are the references that we have looked into for our project, and we have got quite some ideas from these papers, which will effectively utilize for further developments of a project. And yep, our team, as Shreyas has mentioned, comprises of myself, Shreyas, and Rutvik. And our main objectives of learning, the first one we began with learning computational geometry. It was not so new, but we got introduced into it by Ritwik, and we have learned about diagonalization techniques to divide a polygon into n number of triangles or trees or vertices. Uh, or Voronoi map, vertices as represents the Voronoi map, to determine an optimal number of static guards as well as mobile guards right now, and hence a Watchman route. So we are coding the program in Python on our own, and of course we are using some reference material as well. And yep, as Shreyas has mentioned, we have quite, yeah, we have quite some work done in this area, and we can hopefully make use of it for the development, for the better development of our project. And we also have the opportunity to implement algorithms such as APF, RRT, RRG, RRT star, and so on, and ENE star, and so on, to compare our results with that. If feasible path is found in the other algorithm, using the other algorithm, we can compare our results and put out a chart by explaining which is better and which is what are the drawbacks and what are the advantages of every algorithm, and possibly ours work the best. Yeah, ours work. PPF works much better, hopefully. And the deliverables are we have three main goals, which are the deliverables. First one is an optimal Watchman route in the presence of mobile guards, and the second one is optimal Watchman route in the presence in a polygon with holes or obstacles, namely. Uh, in a polygon with obstacles, and our third extended goal, or our second extended goal, and our third main goal is to solve the Watchman root problem in the presence of an intruder, and to track the intruder, and also to determine the optimal number of cards while keeping the computational time and the time taken to traverse the path minimum. So here the workload has to be managed between the guards to track the intruder, as well as to track the path, as well as to monitor all the vertices. And that's it. Thank you so much for listening to our presentation, and we'll come back soon with some pretty good work. Thank you. Thank you, Professor.